Meeting today will be recorded. We have a webinars playlist on our YouTube channel that you can go to. We put all of our webinars on that channel, and you're always welcome to go there and view at your own convenience and then ask any questions. You can submit any questions to support@adaptsoft.com. Today we would ask, I've put everyone on mute, so I apologize, but we'll ask if you do have questions. There will be a Q&A on the back end of today's training. If you can, just jot down the question and we can come back and revisit it at that time. Today's meeting should last roughly an hour for the content, and then we'll go into the Q&A after that. And also, if you have questions related to anything other than the content in the webinar, please feel free to contact support@adaptsoft.com. Today's webinar is going to focus on a two-way RC flat slab using Adapt Builder. And it's really intended for those who might be new to the program or may not have used it consistently, maybe more intermittently, and you just want a good refresher on just the main process for modeling, setting up criteria, loads, load combinations, and going through some of the design features. Now, this is not all inclusive of what is kind of under the hood, if you will, in the software. We're kind of just outlining the main workflow for the design of a two-way slab. And today we're going to start with importing both a Revit model and also showing the DWG import. Some of you are probably really familiar with this process. So, and then we'll actually use the model that we convert from a CAD file. After that, we're going to talk about adding loads, defining combinations. What do the combinations mean? What do they do in terms of their, what we call their analysis and design option type? And then take a look at some of the criteria, which is a little bit different than criteria for two-way PT slab. And we concluded a two-way PT slab webinar last week. So those are, again, on the YouTube channel if you're interested in seeing that. We'll talk about the punching shear check, take an initial look at deflection, just the linear elastic deflection that's a result of the modeling, and determine from there if we need to increase the slab thickness, for example, for the model. And then we'll go into strip modeling. Now, one note about strip modeling: we've introduced a new, much more efficient method for generating design strips, and that's upcoming in version 2019 later this summer. We have added a video online. You might want to check it out. It's only about 5 minutes, and it goes through kind of a very quick example of how to generate strips in the upcoming version. The notion of, for those of you who are familiar with modeling, the notion of splitters is completely vanishing from the software. You can still use a splitter, or what I'll call a boundary, just to limit the extension of a design tributary, but the need for them at ends of support lines is completely going away. So that, I think, hopefully that'll make several of you happy who use the software often. Finally, we're going to talk about meshing analysis and just look at some design results. And hopefully we'll get through all of that in the next hour or so. So we'll go ahead and start now. I'm going to start with a Revit file. We have a model here. We have a larger floor plate at the bottom, and at the top few levels we have something that's a little bit condensed and reduced. We're going to mainly look at this bottommost floor plan here. We have the Adapt Revit link installed on our side, so we're going to use, this is the Adapt 2019 Revit link. We're going to export this Revit file to Adapt, and we're going to use this Revit it's under Analyze, Adapt. There's an Adapt panel when you install the Revit link here. We don't have custom column names, so we'll just use the default B&H column parameters. The program will show us what levels will be exported from Revit to Builder. If you want to limit this set of levels, you can always use structural. If any of your levels are actually tagged as structural levels in Revit, you could limit it. Here, none of them are, so no levels will be imported. And then active means if you have a structural component that is interpreted by our IMP format and it's referenced from a level here, we'll import all the levels that actually reference those components. So we're going to use active. You can see under the component tab, there's several components listed. This is read-only. You can't really filter anything out yet. That all happens on the builder side. And there are no load cases. There are some combinations. I'm actually going to select these. These are selectable in terms of the combos and cases. I'm going to throw those back over here. I'm going to set everything up inside a builder. And I'll go ahead and export the file. So I'll call this to adapt. It writes this as an IMP file, which is really an exchange format that we use for different programs. We use this for ETABS integration, Tekla structural designer integration, adapt integration, and even between adapt versions of the program. So if you're changing one file from a builder model to another builder model, you can use the IMP format. I'll go ahead and save that. I'm going to minimize Revit. And in Builder, we want to make sure we have the right selections made in the splash screen. So you can see that I've deselected PTRC. We don't want to model post-tensioning, for example, in this case, so I'll use only the RC mode. We'll say OK. And we had Floor Pro also selected there. That's also critical to have Floor Pro selected. That allows us to design floors in the program, elevated floors or slabs. You can see it also notes what modes you're in here. We have Edge with Floor Pro, RC mode. So that also gives an indication. So I'll go ahead and just save this file. We'll do a save as, and we'll put this over here. Okay, and I'm going to go to File, and I'll import an IMP file. This is the file we saved to adapt.imp. If I choose to import all of the levels, then I can just select all. Notice if this is selected, none of the components are active. You can't filter them. If you select only one level, maybe I just want to select plane 2, for example, then I can filter what components come into the model. You can also use this in fairly constrained way in doing some round tripping with Revit. If your Revit model it changes, then technically you could write a new IMP file, save that file, import it into an existing builder model, and you can use this filtering to, let's say, import maybe only columns for level 2, or excuse me, for plane 13. So, but we would also want to update. We don't want to create a new model. We would update an existing model. I might update plane 13 from the Revit file, and the reference file inside a builder technically would also be called, hopefully, plane 13. It doesn't have to be, but in this case, notice we have current, bottom, and top. Those are the default level names for this new file that I'm creating. So we're going to create a new model, and I'm actually going to bring everything in because I want to talk to you about the notion of single level versus multiple level in the program. So we'll import everything. There are no loads or load cases and no load combinations. So we'll go ahead and say OK. Once we enter the modeling space here, you can see that we automatically go into a plan view in what we call multi-story mode. So multi-story mode is this nice button here. The one next to it is single level mode. Single level versus multi-level. And these are important to note because it not only does it graphically represent what mode you're in, but analytically, if I analyze this structure in multi-level mode, the program assumes supports at the base of every vertical stack. So at the very base level of all the column and wall stacks, we use a fixed condition. And that can be changed in the criteria settings for multi-level fixity and single level fixity. I'll show you that here in a moment. If I switch over to single level mode, then I decide which level am I working on, which level do I want to actually analyze and maybe design. So here I could navigate to a particular level. I can go down to level 2, for example. This is a level we'll be working on today. And if I mesh and analyze this level, then the program uses a default condition which is different than the multi-level mode. It's actually a fixed roller at the base, which can also be user defined. It can be edited by the user. So if we go to criteria, analysis, and design options, the user can set up your support conditions here. For single level, it's set to fixed roller by default. For multi-level, it's set to fixed by default. And you have the ability to basically interchangeably analyze a structure, multi-level mode or single level, without ever leaving the program or leaving usage of the program. There's a question, if we want to design the footings, would it be good to switch to mat? Yes, if you wanted to design the foundation of this particular structure, just to give you, this is actually covered, I think, in another webinar, but just to give you a very brief introduction here, let's assume we're only looking at self-weight because I have yet to load this model. I could actually say I'm going to select all of my slabs. I'll just throw on some loading here, and we'll say let's use 20 PSF dead load, and I'll add live load of 50 PSF. Okay, and before I mesh this, before I do anything analytically that is really related to finite elements, I can do this, perform load takedown. So this is based on the geometric tributaries of each of the vertical elements. I'll calculate the tributary regions for the multi-story model, and also I'll just go ahead and recalculate the loads in each of the different elements vertically. So that's, right now we have an accumulation of load down to the base of the structure. If I navigate to plane 2, for example, I'll go to the default display, and I'll go into my results browser, and I'm going to turn on, under analysis, load takedown, cumulative loads. So for example, at this column here, there's 40 kips of dead load, 100 kips of live load, and 283 kips of self-weight. And those tributary loads, as we call them, can be used to do different things. I could design the column using those axial loads aside from, or I guess in lieu of, the FEM loads. I could also apply those loads to a foundation. So if I go down to the next level below, in single level mode here, I could go in, I could model a foundation. We'll just say it's a mat for sake of time in the example, and then we'll say this is, I don't know, 20 inches thick. That probably won't work, but we'll use it anyway. I'll define area spring. Okay, and when I define that spring, I'll make this setting, I'll say it's compression only with some subgrade values, subgrade modulus values there. Now, if I want to analyze this level, which is the bottommost level in the stack, then I have to use adapt mat. So that was the question: what do we do when we want to, evaluate this? I'll close the program. I'm going to reopen Builder. I can utilize the exact same model. I don't have to create a new model. I'll just switch this to mat. And this is used for foundations. So that was the question that had come up. And if that's the wrong model. Let me find the right one. Okay, here's the one. So now we have this mat. Remember, I'm in single level. If I go to multi-level, there's the rest of my model. And inside of mat, it could be a mat slab, it could be a footings, spread, continuous, pile caps, different types of foundations can be modeled here. If I analyze this level now, I'll just mesh this one level aside from the entire building, and I apply the reactions. If I execute the analysis, I can apply the reactions from tributary to this level. I've applied the reactions, and now I could evaluate, let's say, the soil pressure and design this mat based on those reactions. If that was what you're after. I mean, we might also want to include lateral load, which would require us to tap into the finite element engine. But in this case, I could utilize tributary for all of my axial forces. And now, ultimately, you can gather some results here. I'll give you an example. If I want to look at soil pressure for this mat, based on my tributary takedown, we have a pressure map now for that mat. So that's just a very quick, brief review of kind of the cross utilization of multi-story with load takedown, and then also a mat slab at the base. Okay, we've shown the Revit import. Now I'm gonna go ahead and there's another question. While running the analysis, I'm just gonna read this verbatim here. It doesn't have to run in the full building structure mode. No, because you could run this analysis in full building if you wanted to. So if you have multi-story mode, now there's no need necessarily to apply reactions because we're looking at the entire structure. So if I was to analyze this full building, you can see because I have springs at the base of the structure, it asks me, do you want to substitute the springs with fixed supports, or do you want to consider the springs? If I consider the springs, then I have a direct solution. I can run the full building analysis and directly look at the pressures, design the mat or the foundation level. If I use substitution, then the program assumes that the base is fixed, and I would then go back into single level mode like I had done previous, and then rerun single level with FEM reactions or tributary or the envelope of both. So there's two different sources of reactions. There's this tributary load takedown, and if I run the full building analysis, the other set of reactions would be FEM reactions, and they could be different. They're utilizing different technology or utilization of different methodology to get the results for that type of analysis. Okay, so I'm going to close the program. I want to reopen it in Floor Pro mode and get us back on track here with RC design. So any questions, again, please let's try to wait to the end of the meeting and I can answer any questions you'd like, or I can at least try to for you guys, and we can delve into other topics if needed. So all right, I'm going to reopen this in Floor Pro. And we showed the Revit import. Now we're going to do a CAD conversion. We're going to actually use the CAD conversion for the basis of the training. So we'll go ahead and we'll go to File. And I'm just really going to build one level here. Just earlier we had the entire model. Now I'm looking at just one level that we're going to design. I'm going to import a DWG file. And this, again, just illustrating two different methods of building a model aside from just using native modeling tools like grid lines and so on. So we'll use this CAD file. I'm going to calibrate the file, and I'll say that we're going to calibrate a dimension in the model. So I'll use my snap tools and come up here and snap from point 1 to point 2, and we're going to enter this as 20 feet. And then I will zoom extents. Okay, and after we zoom extents, we will start converting this to a structural model. Right now it's just a pancake with no thickness. Pancakes have thickness, this does not. So technically it's not a pancake. So you can see it's completely just flat. It's 2D, and let me go ahead and close Revit. So back in top view, I'll go to the modeling ribbon, and we're going to be using this transformation panel right over here. I can transform anything that is a polygon, we can transform to a component. So I'll take the slab and I'll transform the slab. I'll take my walls and transform walls. I'll do openings 1 and 2, transform those. We have a bunch of other little openings. I'm not going to model all of those today. I'll take my columns. Now, if I don't want to select every single column, I can use what we call the layer settings manager. So if I go to the home menu, I can go under display layer settings, turn all of my layers off, and then I can just isolate one of the layers, which is concrete columns. And I'm going to select those columns, and now that makes it easier to window sweep to select. And we'll go back to model, transform the columns. Okay, so we've built our model essentially from the CAD conversion doing this, and I'll go back to the layer settings and I'll turn everything back on. So now I have an actual structural model. If I go to a side view, we have a model, a slab, columns, walls. I'm going to select the columns and walls and copy them to the plane above also. You may or may not want to do this depending on, I guess, what stage you're trying to capture for the the stiffness of the model in terms of the design. So we'll assume that the columns above are in place, as are the walls, and I'll just use modify vertical. I'm going to copy this up one time, and that copies it to the top plane. So whenever we model a vertical component, a wall, a column, those will go from the current reference plane, and in this case it's the default name is current plane, and it will be modeled downward. So you can see if we double click on this column, we have some properties associated. We have the material that it's tagged to. By converting it from a CAD file, the program automatically creates a section type, which can later be used to do column design. Otherwise, you have to define them in the program, not, I would say, manually, but typically we have to define section types and group columns into different section types, unless we convert it as a CAD file or from a CAD file. Up here under location, you can see this column goes from top to bottom, and there are 0 offsets vertically. So I could offset the slab depth, and it would still be connected to the slab. If it drops below the slab with a gap, you're going to have a disconnection between the two elements in the model. Okay, I'll go back to a top view. I'm using some quick access tools down on the bottom bar. You can also access additional tools from the home menu under the zoom camera, different static view states of the program. And I want to turn the CAD file off. I don't really need it anymore. If it's left on, it can be a little bit cumbersome trying to select structural components. So I'll go up here to the visibility menu, and under the group library, the CAD file gets stored as a group automatically. I'll turn that group off, and now I'm left only with the structural model. Okay, and we'll go ahead and save this as our base model, and I'll just override this one. All right, let me go back to this cheat sheet here. So we've talked about generation. We're going to look now at just adding some very basic loads. This is not necessarily a podium slab. I'm calling it an office slab, but I don't think it really serves that purpose either, based on typical office slabs usually have beams and some sort of beam system. But we'll say it's an office slab in terms of loading. So we're going to talk about loads and defining combinations and some of the criteria. First, I'll talk about criteria in terms of the material settings. So we'll go up here to criteria, and under concrete, we're going to add an additional setting here. So if you want to add additional concretes, I would add, and then you can always override the name. We'll say this is 5,000 psi. Just for the sake of an example, if we make changes here and we want to apply them to a particular component, let's assume that the columns and walls are 5,000 and the slab is 4,000 psi. So I would select the components that I want to change. I would either have to do it one by one, which is a waste of time, or you can select multiple components and change them. Now notice, if you have a section type that is already defined, I cannot change the material in this dialog. I would have to actually go into the section manager, and in the section manager I would define and change the concrete right here. So that's one thing about section types. The material assignment is always defined here. I'm actually going to delete these out, and if I come back to a column, now that option to assign material will be unlocked, and I can change between the two. If I select by type my columns and my walls, we want to change those to 5,000 psi. Anytime you make a change of more than one component, then we have to use the modify selection option. So we're changing a handful of components. We'll say the material for these will be 5,000 psi, and we're done with that. The slab is still default set to concrete 1, which is really 4,000 psi. Okay, we're also going to make a change to the slab thickness. I'm going to call the thickness 8.5 inches to start. For rebar, we define our rebar material here, where we specify the yield stress and also the modulus of elasticity. You can have several material types defined if you'd like. Those then can be assigned to different bars that you want to design or calculate for the slab. So under rebar size material, for example, for a two-way slab criteria, we're going to say the top bars will say are number 6s and the bottom bars are also 6s. The stirrups doesn't apply here to us. This is for beam only. And then the material for top and bottom bars, had I defined a second material, we can select between the two, or 3 or 4, however many you define. We'll come back into criteria here in just a sec. Steel fiber doesn't apply. I guess it could apply if you wanted to introduce steel fibers into the concrete. These are engineered fibers. They're not just some shreds that you get down to the local fabrication shop and throw in the back of a pickup truck. So those are engineered fibers, which are Becker Dramix fibers. They're a proprietary fiber that if you add a fiber material, you get some other options here, and you can actually define what type of fiber you're going to use, and there's some different variables and parameters that are associated with that fiber type that have to be defined. Okay, generic, this doesn't apply. This is for specifying another, just a generic material type other than concrete. So if you were trying to, for example, model a steel column and you had to define that material and then define that type of a section, you could actually define that inside of the program. Everything here we're assuming is concrete. Okay, let's go ahead and add some loads. I'll come back to some of these rebar settings when we get into the design of the reinforcement. So we'll go back here to loading. Load cases. The program has two kind of categorizations for load cases. There's a general load, which is dead, live, roof live, snow load, whatever load case you want to define or add. By default, we have 3 reserved load cases. There's self-weight, which is auto-calculated by the program, and then you also have dead load, and this would be superimposed dead load, and here this is unreduced live load. There's also this classification called building load. This is not applicable when we're working in single level mode. These loads are only solved for when we run a multi-story analysis. So if you have a multi-story frame and you have several, let's say a distribution of story forces on this structure, and these story forces in this direction we're going to call wind X, and maybe they're auto-calculated by the program. They might also be EQX. These types of loads are stored here as building loads, and they're only solved for, again, when we run the model in multi-story mode. So they don't really apply to a single level structure, because when you get obviously lateral loads on a structure, usually unless it's a construction lateral load for some special consideration, usually the building is in service and the load set would apply to the entire building, not just one independent level, in terms of that particular model. So we're going to ignore this today. We'll come back and talk about that in a different webinar as part of our series here, but we're going to mainly focus on these 2 loads for the example. So I'll select the slab. There's different ways to apply load. You could apply point, line, patch as individual loads placed on the structure, or you can map patch loads and line loads to a selected slab, or really a selected polygon. If I drew a polygon on this slab, I could use, for example, this option for polygon, or it could be an imported polygon from a CAD file. If I do that and I select it and I come back to loading and add a patch load at that point, the program will load that polygon. So it's not only just selected slab regions. However, I will apply load only to this slab region. We're going to assume that the loads are 50 PSF unreducible live load plus 15 partition. So I'll add a patch load live. I'm going to add partition here, so it'll be 0.065, and that's going to map load to this selected slab. Loading is always cumulative. So if I went and added a -20 live load to the slab, then the net effect would be 45 PSF live load. So the loading in the program is always cumulative. Every load instance, meaning I'll call it a loading component, can only represent one load case. So this particular load that I've just created, if I go to this view, that is only defining the live load. It doesn't define, if I change this to dead load, then it can be changed, but it can't define both. So I have to actually add another patch load onto the structure in order to define the dead load. And we'll do that. We'll go to patch load, and I'll say the dead load here is 10 PSF. Okay, we could also do a line load. If there's some sort of cladding load on the slab perimeter, I'll do line load wizard, and we're going to say that's a dead load, and it's let's see, 500 pounds per foot. Okay, so these are some options for loading. Again, lateral building, this is more for multi-story. We're going to ignore this block. You could also import loads onto a structure using an Excel file. So you could write line and point loads into an Excel format and import those into a model. This is more conducive, I think, to like a podium type slab where you have a lot of line loads that are bearing on the transfer slab, and you also might have point loads as couples from shear walls or hold down forces from shear walls. Okay, if we want to view loads, we're not going to talk about load takedown. I showed that a little bit earlier. That applies mainly, I would say, to multi-story. load patterning, if I wanted to set up load patterns for this slab, we could use subregions and then add patterns to the slab. This this particular usage of this patterning we have in some instructional videos. I'm going to skip it for today's webinar, again, to get through more of the main content, but you may want to go back and look at that if you're interested in load patterning. Yeah. And then in terms of visibility, we have some new buttons over here that are pretty helpful for quickly accessing loads. This basically turns everything off and on, all loads. We could also classify the loads. I could turn on only line loads, only patch loads, which turns everything on. And then also, if you wanted to categorize a load in terms of the viewing, you could go into the view settings and say, well, I just want to see the live patch load. So this helps you filter it out even further. It looks like there's a question. Let me. Yeah, the question is, do we have the automatic load combination generation tool now, or do we still need the update for this? What Sungyob is referring to is we have a in the works, I should say. It's not been released. It's a load combination generator based on whatever design code you've set. So this is a good segue into load combinations. If we go to criteria and I go to design code, I'm going to define the code that I want to design for. So let's say it's ACI 14. And notice that you can also report crack width in the program, and you can limit crack width. If you limit crack width to a specified amount or distance, then this will be done actually per the European code methodology in the program. You could just report it, which doesn't limit it. This would actually this would give you more reinforcement for serviceability requirements if you limit crack width. But the question was, and I'll actually report crack width, but I won't limit crack width. The earlier question was involving load combinations. So let me go over to loading under combos. Once we set the design code, the program just predefines a few gravity only load combinations. And we have, let's say, service and strength. Okay, service means the program would calculate minimum reinforcement for those combinations. Strength, the program would calculate reinforcement for ultimate moments and axial forces and shears in terms of two-way shears. So the designation here, depending on this designation, that tells the program how to handle the specific load combination. The question was, well, if I have a model that has other types of loads, it might be lateral, it might be other classifications, I may need to have several more load combos. So how do we get those into the model? And the short answer is you have to build them in the model. Okay, once they're built one time, you can use the IMP exchange to actually import load combinations between models. We have this internal tool, again, that has not been released, that would actually calculate, or let's say populate, all of the load combinations into a model. The reason it has yet to be released is because it's all or nothing. If you use it, and let's say you have earthquake, wind, gravity, dead live, self-weight, and snow load, you're going to have probably, I think, 450 combinations produced automatically in your model. And assuming that you have wind and earthquake, our assumption is that it's a multi-story model. And obviously we don't have control over how complex a model is or how simplified it is. But let's just say it's above average complexity and it's a multi-story model and it's 20 stories. And now when you analyze and you mesh, the mesh size is pretty condensed because of the complexity, and you have 70,000 nodes in the model that are being solved for 400 combinations. That can become a performance issue. So rather than just releasing something, without any cap, if you will. We decided to hold it back until we have the ability and the time really in development to develop some interface for the user to be able to number one, choose which combinations you want to include as part of the combination generator. If you have 7 service and 7 strength combinations, maybe I only want to use combos 1 and 3 for an evaluation. We want to give you the option to do that. And then also, we also want to provide the option for wind loading, for example, for the user to say, I only want to consider ASC 7 wind cases 1 and 2, not 3 and 4, which 3 and 4 would potentially create an additional 12 to 24 different permutations of combinations for each combo times however many combinations you're evaluating. So that blows up the number of load combos. So that's the reason it has yet to be released. I'll show you how you can import the file. If I go to File and I import an IMP file, let me see if I can find this file. Let's see. Yeah, here it is. So these are IMP files. Basically, they're models that were created with a lot of combinations, and I actually created these using that internal combination generator. If any of you actually want these IMP files, you can always contact me or support, and we'd be happy to send them to you. So if I, for example, select this one with snow, and I'm going to update this level. I don't want to merge slabs. I don't want to import anything geometrically. All I want to do is import the combos. I'll say import all, and I'll import these combinations into my model. My model is still in place. The only thing that changes is the load combos. You can see this takes a little while to open now because I have, I think, 400, maybe right around 400 combos in the model now. $358. So now I have combinations for wind, for seismic, and ULS and SLS combos in this model. So again, once a set of combinations has been defined, you can always import those into a different model using IMP. You could also save them as a template file using this option under File, Save as Template, and it will store those combinations as a template. When you go to create a new model, you can actually select that template for use. Okay, now I'm going to actually go back to ACI 2011. What does that do? That wipes out the combos. Okay, so we are adding an option that allows you to restore the combinations if you change the design code, but you'll notice that actually wiped everything out, which is okay for this model. For this model, we're going to create we want to check the model for cracking under sustained load and long-term effect. So I'll create a basic set of combinations to do this. This could be more complex, or you could have more combinations, to predict different stages of load being applied and whether it's cracked under that stage and what the long-term effect is at that particular point in time. But I'm going to use this option to add a long-term deflection combo, and it's going to ask me for the creep factor. I'll say it's just 2. We're going to predict this out in time, 5 years, let's say. And we have now added one sustained load combination, which is called cracked deflection. And so the program will check this combination for cracking. That's all it does with it. It doesn't add rebar. It just checks under this load premise what's the cracking in the slab. And then also the long-term really just takes the creep factor plus 1 and multiplies it by sustained. I could manually create sustained and long-term combinations and combine the effects of different combos. Okay, there's a question. It says, I have a quick question. In most of my models, I do service load combination for earthquake load 2, so I check the soil pressure. However, if I define it as a service total load, it will design the slab for minimum reinforcement for earthquake loads 2. Do you have any suggestions on how to define ASD load combinations for gravity and lateral separately? The short answer would be run the batch of combinations separately. Then you'll have to basically combine the results of both. If it's a two-way RC slab, it shouldn't matter because the minimum reinforcement that we have programmed for ACI is just minimum temperature shrinkage rebar. So it's not impacted by the stress in the slab. If it's a post-tension slab, then the minimum rebar for positive bending regions is impacted by the stress level. So in your case, you would have to run the combinations or the model with only gravity level combinations, for example, determine the amount of rebar, and then without gravity and with lateral and determine the rebar. It would have to be run twice. We do have a request to actually be able to merge designs from two different sets of runs, so we can basically envelope all rebar from different analysis runs. Or we would actually tie it to usage case. So usage case 1, you would actually be able to define a set of combinations. Usage case 2, another set, and then we would merge them in the results in terms of the rebar output. And also, I guess, for stress checks in this case. Okay, so let's go ahead and close combinations, and we're going to kind of reorient ourselves here. We've added loads, defined combinations, and done a little bit of criteria. We're going to run the model, and we're going to check the initial deflection and also do a punching shear check to determine, are we kind of within the ballpark of where we think we need to be for the slab thickness. So I'll go up to analysis, and I'm going to mesh the slab, and I'll use the default settings here. And I'll execute the analysis. I'm going to execute this for all combinations. It should run rather fast. Okay, and then let me go back to my default display. I'm going to turn on the service total load deflection. So we see we have deformation, and we can see that our max deflection is out here in this bay. It's about 0.61 inches, and maybe our deflection limitation, maybe it's L over 240 or 360, whatever is imposed on the design. And we say, is that going to actually work when we consider long-term deflection and cracking? So based on this particular run, I can't really say whether or not it will work based on those other two factors, but I could, determine maybe if I just do a quick approximation, maybe I multiply this by 3 or 2.5 to predict long-term effect. That's creeping up around 1.5 inches of deflection, maybe even more. So whether or not that works for our, our bay size and the criteria that you're using, you would make an evaluation. Maybe the slab may need to be thicker initially. So we would modify the slab thickness and maybe rerun the analysis to whittle that down. This slab is small enough, I would actually recommend you just go through the entire process of design, the entire workflow, and even just look at the cracked long-term deflection before you actually come back and change the slab. But this is one thing that you can do. You could also use a manual design cut in this case. I could go up to floor design, and let's say I wanted to look at the deflection along 3 paths. I wanted to look at the deflection along this in this bay here, I'll look at the deflection along here, along this path, and maybe along here. Okay, my purpose of generating these cuts is only to look at the deflection in this case. So I designed those cuts. This is aside from setting up support lines and design strips. And for those cuts, I can now go to the manual design section information and look at the deformation. And you can see for, this is for service total. Let me just flatten that out. Yeah, this what this is doing is it's taking the deflection, which doesn't seem up here correct. I'll have to check that, but there's obviously zero deflection here. Let me pull that out to there and to there, and I'll redesign that one. Yeah, it should be taking the distribution of there. This is more appropriate right here. So if you look, this takes the distribution of the deflection along this path, and the total deflection is 0.54 inches, and it divides it by the span length. L over 661 is the outcome there, 961 here, and that's based on service total. This cut, I'm not sure what's going on there. I'd have to review that, but this is typically what the output looks like, some distribution of displacement along the contour or along the cut line, and then the L is actually represented by this length of the cut line. So it can be used for this type of just quick analysis of a span. If we wanted to check the punching shear for the same result, we'll go to floor design, and I'm going to set up my shear design settings. We're going to use studs, and I'll set this to 1/2 inch diameter studs. The default is 2 rails per side, but in reality, I'm going to limit the number of rails, or the spacing of rails rather, to 2 times the effective depth used. And then we're going to provide uniform studs, and I'll just execute the punching shear. And I need to switch over to the envelope of strength, or I could do an individual strength combination here. And we can now look at the punching shear result. So it identifies where we need, whether a column passes or it exceeds the code. You can see there's one column here that exceeds code, and if that's what essentially dictates the thickness of the slab, then we might have to dig in further to see how's the program treating this column. Well, if I go to condition, the program is actually assuming that column is a corner column because of that notch in the slab. So it indicates the critical section by this dashed line here. And it assumes that there's a free edge here and a free edge here. So it ignores this distance in terms of the critical section. I guess it would do something like that. If I wanted to extend it out and include this as part of the critical perimeter, I could then kind of whittle the result a little bit. I can go back to shear design and say, okay, the program is conservatively treating it in the manner I just described. Now I'm going to ask the program to extend the critical section out to the slab edge. And I'll go back and I'll just re-execute the result. And now it actually works. Okay, so the stress check now allows me to reinforce that if I assume that tiny little extension. So if we wanted to go further into result of punching shear, we could see, what is the rail requirement and what's the reinforcement requirement for the columns. We're going to assume that we're okay with reinforcing for punching shear. We just were checking to see where we actually exceed the maximum allowable stress for which I think is 8 squared F prime C for for two-way shear in the slab. Okay, so we could get further into punching shear results both graphically and also through punching shear results either in the Excel data dump or just some reporting options here. Okay, so we'll continue with the slab thickness that we have currently laid out. Now we need to generate our strips for this model. So I'm going to turn off this. I'll go over to floor design. You'll notice under criteria, really quick, under analysis and design options, there's an option for the program to generate middle strips in addition to the strips that we're going to input, which will be the column strips. So we'll see kind of how that output looks, and then we'll decide whether or not we want to turn that off and manually generate our strips. So I'll go through this. We're going to set up our X direction strips first. And I usually start out of the slab edge and I come back and I adjust those. And again, this process will be a lot easier once we get into the next version of the software. But for now, we're kind of limited to what we can do here. And it's not too bad. It's just, it can be a little more time consuming, but I'm going to, now this is subjective. I mean, I could ask 5 of you to lay out strips and probably we would get 5 different answers. So I'm just trying to lay out my column, let's say my column strips. I'm sure some of you may disagree with how I'm doing this, so but that's okay. Okay, and then I'm going to add a strip here, and I might add a strip like so. If I want rebar in this between here, I would need to add a strip there, but we're going to basically just block this out of the design of the slab. Okay, so that's done. I can now come in, and if I wanted to, I could go back and just set those back perpendicular to the slab edge, just to clean that up a bit. This will be automatically trimmed anyway for the new upcoming version, so that'll be a nice improvement. And then here, something like that. Now we also need to add splitters in this case because we have some support lines that terminate kind of in the slab or away from the perimeter of the slab. This terminates here. If I'm breaking this up into, let's assume I'm not using middle strips and I just want full tributary strips, I would need a boundary here so the program would know to break this strip up like so, and it knows where to stop this tributary because that point, right now it doesn't interpret that point as an extended or projected boundary. So we have to add a boundary, which is called a splitter. I'll add this X direction splitter from that point vertically to this continuous line above, and then also down to the line or the support line below. So these support lines are really just splines that the program uses to generate the column and the middle strip tributaries. Okay, so those are the only splitters. Everything else starts and stops at the slab edge. And I also want to bound out this core. So I'll just put a splitter there, one there, and I'll go from side to side now. So I'll do one like so. And like this. So I completely isolate this using splitters from the rest of the slab. Now if I generate my strips without the use of middle strips, I'll go back and generate the sections. You can see this is pretty straightforward with how the program has cut the slab up into our strips. These are, again, full tributary, meaning the breakout is kind of half the distance to the next or the adjacent support line. I'll go back now and turn middle strip on, and the program is going to attempt to add middle strips in between each of our column strips. So if I regenerate those design strips, you can see the program automatically adds a strip here, and its extent is projected from the shorter support line on either side. So this point that you see here really is where this one stops. This point is where this one stops. And so this support line actually extends all the way out, this cut. How do I manipulate that? I could just extend this out of the slab, and then this middle strip would actually come out to the edge of the slab. So there are ways to manipulate the output. I cannot post manipulate my middle strip, however. So I will delete these, and I'll make two modifications. I'm actually going to take this and just extend it like so, and I'll take this one and just extend it out of the slab like so. Okay, this one also, maybe I'll do that. It's technically it's not connected to this support line on the opposite side of that notch. And we'll regenerate the strips. Okay, so now you get a middle strip here, one there, and this one cuts off here because there are two discontinued support lines there. But that's okay. This is more I think appropriate. You can also see this middle strip actually passes through because this support line on the top and the bottom is continuous. So that we're just going to live with that. There are no design cuts in there, so the program's still not designing anything for that direction. Now you could also manually create your middle strips. You're not bound to having the program use the automatic option. You can turn it off, and then we would go in and actually draw in these middle strip support lines also. Okay, so that's the X direction, and I'm now going to turn off the display of those, and I'll do now the Y direction. Okay, so we'll go ahead and we can rotate our reinforcement. Once we calculate the rebar, we can rotate the reinforcement so it's orthogonal versus along the support line. So that's a kind of a post analysis and setup of support line process. This one I'm actually just going to take through the notch here and something like so, and then here I'm just going to create another strip along that path. Or I could just allow the program to generate a middle strip between these two, which would be along that path anyway. So that might be an easier option there. We're going to create our splitters for the Y direction. So again, these are placed where we have support lines that discontinue. Like here's another location where that happens. You can always use backspace to undo if needed. And then we're going to again bound out the main core area. Okay, and I'll generate the strips again. So this will generate middle strips and column strips for both directions. We've already looked at the X direction. We're going to say that's fine, and then I'll go to the Y direction, and we're going to assume that this is what we want also, even though it may not be. We may have to make some revisions here if we don't like the outcome, but we'll use this for this example. Okay, if you want to view the strips differently, maybe you want to look at them with their tributary outline, you can turn on the tributary outline. You can go to reports under design strips and look at the hatched view for example, of all of the design strips in the model. This is more of a reporting mode versus just kind of graphical output in the user interface. It looked like there was a let me just open up the meeting here. There was a question. If there are many random shape openings on the slab, do I have to draw the splitters around each opening manually? Or if they are appropriately modeled as opening, can the software recognize them? In the next version, the software will recognize them. In this version, they will not. But that does not mean you have to worry about them. I'll give you a rule of thumb. If you have a support line, let me draw this on screen here. If you have an opening, and let's say you have a support line here and one here, and then one down here. This support line here will be cut, let's say something like this, and then this one will cut down into here. If the section cuts into the opening but doesn't extend out of the opening, then it's okay. The program is not going to do anything with a section that goes into an opening. It basically ignores it. So this is still satisfactory. You don't have to technically add splitters around openings. However, if you have a situation where, let's say you have a you have something that looks like this is way up here and this one's right next to this. That's not good. Let's do that. Now we have this. This comes into the opening and exits out of the opening. So now in reality, when we look at this physically, we have slab, an opening, and then slab. This is like the section of the slab here and here. When the program designs for this, it combines it. It says add this to this, and you get some conglomeration of these two sections. But in reality, there's a discontinuity there. So in that case, you would add splitters around the opening so that you're left, with something that looks a little bit different. You're left with this, and this might stretch all the way down to here, but you don't exceed or extend through the opening. So it depends. Sometimes you might need splitters in this current version, sometimes you may not. Okay, we're scheduled for an hour and a half today. I'll go just a few more minutes here so we can close the loop, and then we'll go to Q&A. So we have our strips. We're going to now analyze design the design strips. So we'll go to, we've already analyzed the structure. I'll actually analyze it again just to refresh. So we're going to analyze the slab. We've set up our design strips for the slab, and we're then going to design the design strips in order to obtain reinforcement. But we also need to be able to use that reinforcement to evaluate the slab for crack deflection. So we've analyzed, and we're now going to design the design cuts. We've already generated them. We're just going to design them. This allows us to gather results for bending, for shear, for axial force, and so on. There's different things we can do with the results. There's actually more things you can do with them in terms of the design strips when it comes to post-tension slabs. Like we can check stresses along the strips in PT mode, but we cannot in RC mode. So after we design the strips, you're always free to go in and look at strip results. So just a quick example, if I turn the strips on, for example, in the X direction, I can go into the results. I'm going to use strength dead and live, for example, and I'll go into design sections, actions, and we can display diagrams. If you're wanting to investigate a certain region and you want to dig into some of the results, what do the diagrams look like for that strip? Ultimately, these are the moments that the program designs reinforcement for. So these might be important to look at in more detail. We can also look at any number of the actions listed here. For stresses, we cannot show stresses along strips unless there's PT, so none of this really applies. It's not, I realize stresses are important, but they're not technically required to be evaluated against some threshold for an RC slab. So therefore, we don't really show them in terms of a design check when you're using Adapt Builder in RC mode right here. Same thing for balanced loading, doesn't apply to RC. Investigation could be useful, so we could go and check the moment capacities and the demands for every strip. So to give you an example, numerically I'm only seeing the max min because that option is selected, but I can go to the numerical display for all, and this will give me the blue graph is the negative capacity for each section, and the green graph is the positive capacity. And you can see it also shows a demand capacity ratio on each one of the section cuts. You can overlay the envelope of strength demand with the graph. So you can see, for example, right from this point over to here, I'm looking at these DCR values. Those are all hovering around 1, which means that strength is actually controlling this design and the amount of reinforcement, not minimum rebar. Once you have a gap, like in this space and maybe in this space before you hit the inflection point, that would tell us that minimum rebar would control. So you could look at those results in more detail also. I could double click on any design cut, go into the design sections tab, and this will give me information about that one cut. Here it actually shows me that I need 5.3 square inches for strength distributed over that cut to meet, the ultimate bending design. And that this is being designed as a two-way RC slab. The DCR is 0.99 based on the addition of that rebar and the moment capacity generated from that rebar. So that's more of an investigative mode you can tap into for the design. Okay, so we've talked about the modeling of support lines and design strips. We meshed, we analyzed, we designed the sections. We've talked about a little bit about graphical results in terms of what you can access here. These are all based on design sections. You can also look at deformation along design sections. So for, let's say, service total, I could check the ratios of the span deflection along every strip. And you can see this actually shows me the integrated deflection along the path of the design cut. The program will take this span length from here to there. There's 2 vertices, and it takes this maximum deflection, 0.45, takes span over 0.45 to get this value. And it code checks against, in this case, the default is L over 360. So if I go to display in the result browser, I can change that threshold. Maximum span deflection ratio is at 360. You can modify it to 240, 480, whatever it is you want to evaluate that combination that is selected for. It would check it against that number. Okay, and you can see there's actually some locations where it's defining a span. Okay, so this is a unique case here. This is a middle strip, so the program has actually created a small span along that middle strip. The span is defined by that point and that point. So the maximum deflection between those 2 points is around 0.28 inches downward. So it's taking that distance over 0.28 and giving you this. So this is more of a false alarm, if anything, because of how the program generated the middle strips and the points along the middle strip. This might be a case if you're really relying on these deflection results. This could be a case where you might actually go to using manual input of middle strips versus having the program automatically calculate them, because as the user you can define the input of the vertices that define the spans along the strips. All right, and then last thing we're going to look at very quickly is the crack deflection. Once I've designed the sections, I can go back to analysis, run the crack deflection check, and the program will give me obviously deflections based on whether the slab is cracked, and also show me the loss of stiffness for the slab. So this is a post process that has to be run after section design. It's actually inactive until you design the design cuts. I'll go back and turn off that display of these results here. And if I go to loads, remember I set up sustained load as my crack deflection combo. So if I click the sustained case, this is the deflection of that combination without, with I gross considered, no cracking. So we'll go to deformation, and we can see the max deflection for sustained is 0.51. If I come back and check the cracked condition, it's 0.71, which tells me somewhere it's cracked, the slab is cracking. And if we go back to analysis under the selection of cracked combination, we can always check the reduced rotational stiffness about X and about Y. This will give me a map of the reduced stiffness between both about both X and Y axes. By the way, this is inactive in this version. This is build 2. We're fixing it for build 3. You actually have to go into this viewer to check this. I forgot about that. So inside of this analysis viewer, this is kind of a legacy results viewer. I would check cracked, sustained. Under slab actions, reduced rotational stiffness. You can see there's some loss of stiffness near these columns where we have these contours, and we're losing about half stiffness maximum in some of these spots for bending about X, and about Y, it's also within that realm, about 1/2 IG. So this kind of gives indication where the slab is cracking based on that cracked analysis. Ultimately, we want to know what the reinforcement is, so we can, under floor design, calculate the reinforcement plan either for the full envelope or envelope of service strength or individual combos. And here, this is the layout of rebar. Here it looks a little messy only because by default we orient the bars based on the position of the support line. I could recalculate bars with respect to the global axes X and Y, and this just repositions and reorients the bars here. So if you wanted to whittle the bars down in terms of looking at top versus bottom, X versus Y directions, we can use the rebar settings, and under the display manager of rebar we can isolate different directions and different top or bottom settings. Okay, so there are other options here where maybe we say, well, we're not going to specify these bars as is, we're going to put in a top and bottom mat of reinforcement. And you can always add a mesh of rebar. For example, if I select the slab and add a mesh of number 5s at 12. Okay, this is a bottom mat. We're just using the default cover, by the way, which is set here under the criteria for bars, 1 inch. And then I'll do a default mat for top bars also, which will be 5s at 12. And that might be a little much for this, but we'll say there's now a base mat of rebar in the slab. And if I turn on the settings for showing that base under the symbol setting, this indicates there's a top and bottom mat. Now I can redesign the sections with the mat in place, and the program will show me what's in addition, what is required in addition to the mat of steel for this slab. Okay, so that's that process is done. I'll come back and regenerate the envelope in addition to the mat, and this is what's required on top of the 5s at 12 for the slab. Okay, we'll go ahead and we'll stop there for today, and I'll just open it up to questions. If you have any questions, you can always type it into the chat. Let's use the chat box to ask any questions, and we'll take just 5-10 minutes to answer questions. If there's not questions, I'll conclude, but I'll wait here just for a few moments. And for those of you that need to exit, I really appreciate it again, your participation. You can check the video if needed at youtube.com/adaptsupport. The question was, for crack deflection, does the program include the reinforcement contributions? It includes it, I would say, indirectly, because we use the kind of the bilinear relationship between IG and I effective, which is dependent on the cracked moment of inertia, which considers the presence of the rebar. But in terms of a long-term multiplier, there is a I would say, I'll call it a correction factor, or a factor that is using the contribution of compression rebar. Our long-term multiplier doesn't consider that, but the actual cracked evaluation of every design cut considers the rebar only for the calculation of cracked or cracked moment of inertia. The program, Marcus, does not, another thing to specify, the program does not consider the rebar in the overall stiffness matrix of the solution. So that only defines the stiffness of the concrete components, not the reinforcement. Other questions? Yeah, good question. The question is, if we define stiffness modifiers, we don't need to check the cracked deflections. I would say that that's true. So one thing that we're going to be doing with the program that will be nice is I'll kind of map this out for you. If you check crack deflection, this crack deflection can actually be stored as a usage case, meaning at every node we know what the reduction factor is for the moment of inertia. So if we store that as a usage case, the user could then rerun the analysis again with this usage case and get a new solution for the model. So that's something we're working on, and a user could actually, go through multiple cycles and converge on some state where you don't have any additional cracking. But you will be able to store a crack deflection solution as a usage case in terms of the stiffness in a future, hopefully in version 2019. The question is, even though we specified the opening and added splitters around the opening, rebar has been designed in that area, and can we avoid mesh reinforcement at the opening? Yeah, if you can, you can avoid mesh reinforcement in the opening if you don't use the wizard. So if and some of this rebar that creeps into here is really just based on some extension parameters in our algorithm for generating the layout. But in terms of the mesh reinforcement, instead of me using the wizard, I could just create a mesh, and I would literally have to map the rebar. This is just like a polygon input. I would create a mesh maybe over here. I'm not going to place it right on the slab necessarily, and I would create a mesh kind of in this region here. So you might create two mesh regions and nest them around the opening. All right, well, I'll go ahead and terminate there. We appreciate everyone's attendance. We're having another webinar next week. For those of you who have signed up, we'll look forward to seeing you there. And then again, you can always come back and revisit the video at your leisure on YouTube, on our YouTube channel. Thanks again, everyone. Goodbye.